Hello and welcome to this tutorial for Fox 2020 on lower bounds for statistical inference in distributed and constrained settings from wherever you are. I'm Clément Cannon, and this tutorial is joined with Jalev Acharya and Iman Choutiaghi. And I'm in charge of the first part, which is going to be what is this all about? So let's dive into that. As the title may hint, this tutorial is about techniques and recipes for distributed learning and testing under some types of constraints, some types of general constraints. What does that mean? Well, first, learning and testing. Here we're going to be focusing on parameter or density estimation. And so that's the learning part. And for the testing part, on goodness of fit or identity testing, or more broadly speaking, hypothesis testing. So in the first part, learning, you want to estimate a parameter. And in the second part, you want to distinguish, to test whether the underlying distribution has something you're looking for. And the constraints part is that in contrast with the usual statistical setting where you have access to the observations, the sample, here there are some constraints that apply individually to each sample, so local constraints. And they can be of many types. They can be memory constraints. You can only store so much about each observation. They can be communication constraints. You can actually send only so much. You have a bandwidth issue about each observation. There could be measurement constraints. You can actually not fully observe the data itself. You are constrained to the way you can measure it. Or they can be privacy constraints. You do not want to divulge too much about the data. So those are only a few of many constraints that fall under this general umbrella. There are more. You could think of various types of local noise, etc. Here, for this tutorial, we're going to focus on two of them, the local privacy constraints and the communication constraints. We're going to get back to that. So there's one word that remains, the distributed part. And let's just say this is my motivation slide. We no longer have, in many cases, all the data centralized in one particular case, which I'm going to refer to as the centralized setting. Instead, that data is distributed across many machines, many devices, many users, or just, you name it, many processes, each of them with its various specificities. And so we're going to consider each of them having their own data, and the goal is on aggregate to perform in a distributed way the statistical task at end. So estimation or testing on the data, which is assumed to come from some unknown probability distribution, prior, if you will. So again, that was the motivation slide. Assuming you are motivated, let's go and see one example of what that can be. So here's the very fundamental and maybe seemingly simplistic example, high-dimensional Gaussian. You have n observations from a high-dimensional Gaussian. Let's even say it has spherical covariance, so high-density covariance matrix. You just don't know the mean. That's known as the Gaussian location model in some of the literature. And your goal is to learn that mean mu, unknown, to, like the usual suspect, L2 error epsilon. Epsilon is a distance parameter that is given to you. So without any constraints in the centralized setting, it's known that d over epsilon square samples are necessary and sufficient for that. There are various proofs of this fact. The upper bound is actually amazingly simple. The empirical estimator will do. The lower bounds, you can prove it using Aswad's lemma, Fano. Again, there are many, many variants of that. With one little issue, though, they break down as soon as you go in the non-centralized setting, in the setting where you're distributed with constraints. But as stated, this centralized setting theorem is considered, depending who you ask, as folklore, easy, or just yes, of course. Which brings us to that question: how do we prove an analog under, let's say, local privacy? Again, I'm going to give the formal definition later. Don't worry too much about it if you're not familiar with what local privacy is. What about communication constraints? Can we prove easily how many observations are needed under various constraints in that distributed setting? With or without interaction, can the users actually go back and forth or not? All those add difficulty to the task of proving the lower bounds, and also, in many cases, the upper bounds. So here's the type of theorem we might want to And hopefully by the end of this 4-part tutorial, you will be able to prove using the techniques that are going to be explained and detailed later. But under row privacy, so row is a parameter, think of it as a small positive constant. Under row LGP, the number of samples that are necessary and sufficient now for estimating that mean mu of an unknown Gaussian is d square of epsilon square rho square. So basically you take what you had before and now there is a blow up factor, which is going to be d over rho square. So again, this is an example of things that we might want to prove, and by the end of this tutorial should be able to prove. So in a more refined and abstracted fashion, what we want are reusable techniques to establish lower bounds on the sample complexity of many or every, depending on how ambitious you are, such distributed constrained statistical problems. And in various settings, as we will see, there are several options. I kind of alluded to that with the interactive, non-interactive parentheses a bit earlier. So that's our goal. And well, before trying to tackle that, after all, I'm in charge of setting the stage, so we will need some definitions. Bear with me. Hopefully it's going to be worth it. Let's start with modeling those constraints. So, I'm going to use the formulation from a recent paper with Jadev and Imanshu. How do we model the constraints? We've got n users. Each user, so user I, observes xi from that unknown distribution. Independent samples, we've got x1 to xn, user I observes xi, and we'll send a message yi to the world. Depending on the model we're in, it's going to be to everybody or just to the server, etc. So user I observes xi, sends message yi, where xi lives in something that is going to be denoted that calligraphic x, that's the domain of the unknown distribution P. And calligraphic y will be the message space. That's where yi lives. And we can formalize that in a very information theoretic fashion as that channel here, denoted wi, which corresponds to user I. So xi goes through that randomized black box yi and becomes yi. wi and becomes yi. And here I put those dice here to emphasize the fact that this channel is randomized. If you prefer, you can just see that as what it is. So it's a Markov kernel, but basically it's a conditional distribution that given x will give you the probabilities for each message. So this is wi of y knowing x is the probability to observe y when the input is x. Now here come the constraints. We will have that calligraphic w, which is a set of allowed channels. So we won't allow any type of such randomized channel, but just a subset of them, and that will model the constraints. That will capture the constraints we are in. So again, you start with, I want to prove such and such result under for this task, but under like some constraints. The first step will be how do we model those constraints and to come up with the relevant set calligraphic W for that. Now, given that calligraphic W, the algorithm will dictate how the ith user will choose their channel from that set. So that's just the protocol that says like, okay, your user I will pick that channel and run your observation through that to get this message. So in case this is a little bit too abstract, let's instantiate that to our two suspects, the communication constraints and privacy constraints. So communication constraints, the type of the yellow channels will be pretty simple. We've got L bits to send per user. So each user can only send L bits. Think of L as being relatively small, depending on what you want, either a constant or like at least something very restrictive. So each user has a tight bandwidth constraint of L bits. And then the set of channels allowed is just, well, all randomized channels that map into the message space 0, 1 to the L. That's all there is to it. So that's the first example. Let's look at privacy now. So before, as I mentioned, if you're not familiar with local privacy, You don't really need to know much about it to follow this, or you don't need to know anything at all, actually. If you are familiar with local privacy, just please don't hate me yet. I replaced the usual parameter epsilon by rho because epsilon was already taken. So rho is going to be our privacy parameter here. It looks a little bit like a P if you squint, so that maybe makes sense. Rho is a small parameter, hopefully positive, that quantifies how private you want your algorithm to be. So local privacy essentially is I've got data, I don't trust anybody else, not even the server / algorithm I'm interacting with. So I want to divulge as little as possible about my data point as I can. And this is captured by saying that the probability to, given two different inputs, x and x prime, the probability to send any fixed message y is roughly the same, is basically within a factor 1 plus rho. That's that exponential rho here, which is approximately 1 plus or minus rho. So again, if I send the message y, I don't give too much information about my data because I could have sent y with roughly the same probability given two different inputs. And we're going to denote by that calligraphic W subscript rho the set of all rho LDP channels. So just as usual, they're randomized for this to be possible. And we're going to use that crossed I as a symbol for this. So we've seen communication constraints and local privacy constraints as two instantiations of this general local constraint framework. Now let's look at what kind of protocols we're looking. So we've seen the kind of constraints, now the kind of protocols. There are 4 different flavors that we're going to consider in this tutorial, from weaker to stronger. Let's start with the non-interactive private coin protocols. So SMP stands for simultaneous message passing. Think of it as all users speak at the same time. They don't see the other's message. There is no interactivity here. So it's non-interactive. Or like there's that unknown distribution P at the top, which generates n IID samples x1 through xn. Xi goes to user I, passes that through their channel Wi, sends message yi to the central server. There is no interaction, and the private coin stands for the fact that each channel W1 through Wn is randomized, but they are randomized independently. Each user throws their own dice, but there is no shared seed there. Everything is independent. So that's the first one, private coin SMP protocols. We also have public coin SMP protocols, which is almost exactly the same, except for the fact that there is also a common random seed that's available to all users. It's independent of the inputs. So that's that random variable u that you can see. It's independent of the inputs, but it allows all the users to randomize their channels W1 through Wn jointly. So that's the public coin SMP protocols. So still non-interactive, but there is a common random seed or public randomness if you're familiar with communication complexity. Now the third type of protocols we're going to consider is interactive. So now we also have that public randomness, that shared random seed U that is available to everybody. But on top of that, the first user speaks first. So gets their sample x1, passes that through their randomized channel W1, gets message Y1, sends that to the central server, but also to all the other users. Now, second user gets X2, passes that through W2, but W2 now can depend on you, the public randomness, but also the previous message that had been sent before, and so on. So at the end, we've got the nth user that has their data xn and observes all the messages before them, y1 through yn minus 1. Also has that public randomness, and then selects, uses that, passes xn through their channel wn, and sends the message yn. So in that case, again, you have that sequential interaction, and you can think of it as the users speak one after the other, and how they choose their channel can depend on what they've seen before. So this is the sequentially interactive protocol, type of protocol. And that brings us to the last, the blackboard protocol, which is, forget about order, it's just many rounds of interaction. So it's the most permissive type of protocol. It's called blackboard because you can think of it as the users having a giant blackboard in the middle of the room, and again, each of them can come there, write something, go back, and everybody sees the blackboard and can use whatever transcript they see written there to pick their next message. So that's fully interactive. So a few observations at this point are in order. So we've seen 4 types of protocols. Private coin SMP. So the first 2 are non-interactive. Private coin and public coin are non-interactive, SMP. Then sequentially interactive, and then blackboard. And each of these models is at least as powerful as the previous. Why? Because private coin protocols can be simulated by public coin protocols, non-interactive. Then public coin in non-interactive protocols can be simulated by sequentially interactive ones, and sequentially interactive ones can be simulated by blackboard ones. The question is, which ones of these less or equal are tight? Are there separations between those protocols, and if so, for which task? Another thing that's important to mention is, in spite of the fact that while blackboard is more permissive than sequentially interactive, etc., each model has its pros and cons, both in theory and practice. It's not one of them is superior to the other. So for example, in practice, you might have different issues implementing those. You will have latencies if you allow interactivity, or you might or not be able to have that shared random seed sent to everybody. So interactivity might be good to get more efficient protocols, but might be harder to implement, etc. And in theory, well, the more interactivity you allow, the harder it gets to prove lower bounds, maybe the easier to prove upper bounds or not. So each of these models has its own specificities and might require different techniques to analyze. That being said, we've got the constraints, we've got the protocols. Let's look at the type of problems. So I promised you learning and testing here. Let's look at the general formulation. So in both cases, we will have some accuracy parameter epsilon. Think of it as a small positive constant, or at least a small positive quantity. And we're going to be interested in some kind of minimax rates, right? So here we will consider minimax type of questions. Worst case. What is the worst case sample complexity to perform the task we want? For learning estimation, our goal is, after seeing the transcript, all the messages y1 through yn, so that y superscript n messages, we want to design an estimator p hat such that, on expectation, the distance between p hat and the true unknown distribution p is small, at most epsilon. And here the clause depends on some kind of distance or loss that is specified by the problem. So that depends on the setting. It could be total variation distance between distributions, or it could be something else, KL divergence if you choose so, or it could be parameter distance. If p hat and p are in a parametric family, you might want to use the loss, which is maybe like the L2 distance between the means, or the L infinity distance between the means, or the Frobenius distance between the covariance matrices, etc. So D is basically depends on your application. So that's for learning. We also have the testing part. And in the hypothesis testing, we have basically a distinguishing problem. We start with 2 sets of distributions, the yes instances and the no instances, which I'm going to denote H0 for the null hypothesis and H epsilon. And those 2 things should have some separation epsilon, which means that if I take any distribution from H0 and any distribution from H epsilon, their distance should be at least epsilon, where the distance is same thing. It could be a observation distance, it could be parameter distance. It's the same kind of distance / loss as in the learning question, and it's specified by your application. So given those 2 sets of distributions, H0 and H epsilon, the goal is to design a test, T, which will take, as before, the n messages observed, y1 through yn, and then such that it will declare the right set. So if the unknown distribution belongs to H0, then it should say 0 with high probability. And if the unknown distribution belongs to H epsilon, it should say 1 with high probability. And here, let's think of high probability as some high constant probability, let's say 9/10 or 99%, you name it. So those are the two types of tasks we will be concerned with. Estimation, minimize on expectation the distance between the true distribution and the hypothesis you output. And hypothesis testing, distinguish between the case the unknown distribution belongs to H0 and no, the unknown distribution belongs to H epsilon by probability. Oh, before I move on, just a quick point for the estimation. You might be also familiar with the pack learning kind of thing where we want the distance to be small with high probability. Think of those two are kind of interchangeable. So the ones will apply to both settings, but here we will look at the expected distance being small, and that implies in most settings you can think of, that implies the high probability thing and kind of vice versa. So this is for the type of problems. Again, let's instantiate that a little bit. So let's start with estimation. And let's look at distribution learning. What is this? P is a discrete distribution over a set of k elements. So our parameter is k. This is a problem with dimension k minus 1. The probability is simplex. We still have our parameter epsilon. And we're going to look at the loss, that d, to be the total variation distance, which is defined at the bottom of the page if you're not familiar with it. It's basically the total variation distance between two distributions p and q is over all possible events, the discrepancy between p of s and q of s. You can also see of that as what is the probability that the best possible distinguisher specifically designed for those two distributions can distinguish between them given one sample. If you're more familiar with another characterization, it's exactly half the L1 distance between the probability vectors of P and Q, between the probability mass functions. So here in distribution learning, we've got this. So set a discrete set of k elements, a non-distribution over that, total variation distance, and our goal is again to output a hypothesis distribution that will be close in total variation distance to the true distribution with high probability on expectation. Sorry. So for this, just so that we're on the same page, without any constraint in the centralized setting, the sample complexity is k over epsilon square. It's not hard to prove. The usual, at least the upper bound, the usual suspect, the empirical distribution will do it. Observe that it's linear in the domain size. So there's a k, linear in k dependence. So that's the first one, distribution learning. We also have the high dimensional mean learning. So now we're going to look at distribution over a domain of a high dimensional domain. So think of that, for example, RD. And to instantiate that, we're going to be focusing on families like Gaussian distributions, spherical Gaussians, or product Bernoullis, so product distributions over the Boolean hypercube. So here we've got dimension D. P is assumed to be a product distribution over a d-dimensional domain, and it has some unknown mean mu. We're going to look at the L2 distance, so the L2 distance between means, and our goal is to output some estimate of the mean, mu hat, which will be on expectation close to mu in L2 distance. So again, in the centralized setting, the sample complexity, at least for the two families, the two standard families, Gaussians and product Bernoulli, is d over epsilon square. So again, linear in the dimension. So this is for learning estimation. These are two problems we're going to be focusing on through this tutorial. For testing, let's look at the kind of problems we might want to solve. So one of them is identity testing. Depending on your community, you might also know that as one sample testing or goodness of fit, etc. for discrete distributions. So here we've got, again, a discrete distribution of a domain of size k. And we've got a reference distribution on this domain. So for example, the uniform distribution, the simplest and kind of actually hardest example there. So we've got a reference distribution Q on the discrete set of size K, and we're going to consider the total variation distance again. Oh, something I might want to mention. Why is for discrete distribution total variation distance a good candidate for a loss? You might want to use scale divergence, which has other issues. It can blow up to infinity. Total variation distance is always between 0 and 1. Total variation distance, as I mentioned before, has a nice interpretation in terms of distinguishability, which is very useful for applications. It has all the nice usual things you might want. So it satisfies the post-processing, etc., etc. It's a very stringent measure, and one big advantage it has, especially compared to L2 distance, is well, it makes sense. If you look at the L2 distance between two probability distributions, it could actually be vanishing up to 1 over square root k, even though the distributions are disjoint, are on disjoint support. Total variation distance does not have that kind of very pathological behavior. So this is why for discrete distributions, total variation distance is actually used widely and makes a lot of sense. So again, for testing discrete distributions, domain size k, loss being the total variation distance, here our null hypothesis, H0, will just be the singleton corresponding to the reference distribution Q, which is given to you, you know it. The alternate hypothesis, H epsilon, will be, well, it's a composite hypothesis testing question. It's basically everything that is far from this reference distribution. So everything that is at distance greater than epsilon from Q. So in that case, if you want to test whether the unknown distribution is equal to Q or far from it, it's known that square root K over epsilon squared samples are necessary and sufficient in the centralized setting where you don't have constraints. It's a bit less easy to prove than the K over epsilon squared for learning, but it's been known for more than 10 years now, and we have tight upper and lower bounds in pretty much every variant centralized variant you might think of. So this is identity testing. Let's also look at, again, the counterpart for the high-dimensional mean question. So same thing as for the high-dimensional mean learning. You've got, let's say, a Gaussian or product Bernoulli distribution. So again, product distribution of the hypercube in dimension D. Same thing, we're going to look at the loss between mean, distance, L2 distance between the means. And H0 in that case is, well, that unknown distribution as mean 0. It just, if you want to think in terms of signal detection, there is no signal, the mean is 0. The alternate hypothesis will be, no, actually this unknown distribution has a mean that has some noticeable magnitude. The L2 norm of the mean is actually at least epsilon. So you can see that as, well, H0, there is no signal, it's just noise. And H epsilon, oh, there is a noticeable signal, at least epsilon in magnitude. And then in that case, the sample complexity will be, again, for those nice families and standard families we consider, square root D over epsilon square. So again, a square root dependence on the dimension. So that's 2 problems for testing, 2 problems for learning. Before I go further and leave the floor to the next part of the tutorial, some references. All this does not exist in a vacuum. I just did a quick word cloud of bunch of citations. They are not in order. I'm joking a little bit. Basically, there are way too many references for a single slide, or even 2, or even 3. That kind of consideration started a long time ago, more or less with Statistical in '89 on distributed testing, simple hypothesis testing in a distributed fashion. It picked up again in the mid-2000s with a different focus, privacy constraints, local privacy constraints, machine learning motivations, etc., etc. And it's been booming. So there are a lot of works and papers on this. Instead of just giving you a very small taste of it in these slides, we have a detailed bibliography that we're maintaining at this address. There's even a QR code. Please go and visit this website for the references that we are going to talk about in this tutorial. And also, that's the beauty of having a web page for that. We can modify it. So if you think we misrepresented a paper or missed one, let us know. It's an annotated bibliography. We're happy to make any change if we forgot something or made a mistake. So that being said, let me just briefly announce the rest of the tutorial. So this was the introduction. This is done. The second part will be by Jaydev Acharya on lower bounds for estimation, where we'll give 3 different general techniques and frameworks to prove lower bounds for distributed constrained estimation. The third part will be by Himanshu Tyagi, and this will be the counterpart, but for testing. So general techniques to prove lower bounds for hypothesis testing in this distributed, locally constrained setting. And finally, the fourth part, I'm going to be back to complement those lower bounds by upper bounds. It's hard to prove something is tight if you don't have both sides, and give some discussion and a few open problems. That being done, I hope you enjoy the tutorial, and I'll see you at Fox.